So we're going to be talking about exponent rules and radical rules that you'll need to know for the 9th grade exam. Something like this, the way that you would say this is the square root of 25. And the square root of 25 is 5. 5 times 5 equals 25, therefore the square root of 25 will be 5. Okay, if this is like new information to you, I recommend checking out my exponent video that I've made. You can check in the math section of the YouTube page or whatever and find it. It goes a lot deeper into kind of understanding this if you're still a little bit confused or if it's your first time seeing this. But if you're here, then let's go. The square root of 9 times the square root of 225. Remember that you don't get calculators for this test. So you're going to have to figure out how to do this without just plugging it into a calculator and doing the multiplication there. So if we look at 9 as a number, I know this is so obvious to you guys, but I think it's worth going over. So 9 is the result of 3 times 3, right? And so having that 9 in there, we could also say it's the square root of 3 times 3. And that's important because we're going to need to do that for this here. Whenever you see this formation, you should be pretty pumped because it means that you can simplify it easily. Because 3 times 3 is a perfect square. That's 9, right? So whenever you take the square root of a perfect square, it's just going to kick out one of them, right? So the square root of 3 times 3 is 3. And this is going to be really useful on larger numbers like this. So this is what's called a factor tree. We're going to do a factor tree for this 225 just to see what perfect squares live inside of it so that we can simplify it. Okay. So we have 225 here. I don't know which same number multiplies to equal 225. So you need to build a factor tree in order to find out. So rather than thinking what two same number go into it, I see this 5 on the end. So I know that 225 can at least be divided by 5. We know that 5 times 45 equals 225. Now let's break this 45 down. I know that 45 is 5 times 9. We can break this 9 down and that breaks into a 3 and a 3. So another way to say 225 is 3 times 3 times 5 times 5. 3 times 3 times 5 times 5. Cool. Keep that multiplication in there. We have our perfect squares again. I know you may think, oh, well, they're, attached by multiplication. That's fine. That's totally fine. If we take the square root of this perfect square, 3 times 3, just like earlier, we're going to end out with 3. Take the square root of 5 times 5. That's going to be 5. Do our multiplication here. 3 times 15, our answer is 45, okay? So you may have known the square root of 225 is 15. You may have known that, and great if you do. It's always good to know what the perfect squares are all the way up through 20. But if you don't, and if you're stuck, and you're like, I know it's a perfect square, but I don't know if it's 14 or 15 or 16, whatever, you can always break it down, right? They also might give you something like the square root of 54. Now, the 7 times 7 is 49, 8 times 8 is 64, so we know that this is not a perfect square. How do you simplify this? You simplify it in the same way as searching for the perfect squares earlier. You make a factor tree. So we know that 54 can be at least divided by 2. So if it's 2, then that's going to be 7 is 27. 27 can be 3 and 9. 9 is 3 and 3. Okay, so when we say the square root of 54, what we can say is that is the same thing as the square root of 3 times 3 times 3 times 2. Cool? We have our perfect square, so that can leave, and it's 3 times the square root of 3 times 2, 3 rad 6. That's our answer. Let's go to the next kind of similar concept and talk about exponents. And exponents, by the way, are like, you would refer to this and say 5 squared. That means 5 times itself, and that equals 25. Again, if you're like first time seeing this, that's fine. Just go check out my earlier kind of exponent videos where I go a little bit slower into like kind of the introductory type exponent stuff. Now that we're here, though, we're going to be dealing with something a little bit more complicated. So it'll be something like this. B to the 9th times b to the 0 over b to the negative 5th. And a lot of people see this and they get freaked pretty quickly because it's an extremely advanced version of this. But there are 3 concepts that this kind of refers to. The first one is we're going to be talking about that 0 exponent. The second thing that we're going to be talking about is how to do exponents in fractions. Because notice that's b to the 9th over b to the negative 5th. And speaking of that b to the negative 5th, the last thing we're going to be dealing with is negative exponents. 0 exponent. If you have x to the 0, or you have 3 to the 0, or you have 9 to the 0, all of these just equal 1. Okay? So that b to the 0, that just equals 1. Okay? Is there an easy way to remember that? Yeah, just remember it. I don't know if there's an easy way to remember it. I've just remembered it over the years. Okay, exponent in fractions, right? So potentially we could have something where it's like x to the 13th over x to the 5th, right? The way that you can do this, it's the same thing. Notice that it's the same base. We have x and x as the base, so it's the same base. Very important. It's the same thing as saying x to the power of the 13 minus 5, aka this is going to be x to the, don't mess this up, the 8th. Great. Sometimes doing just subtraction in your head and working in pen can be kind of nerve-wracking because I've gone through so many sheets of paper. Just negative exponents. So if you have y to the negative 3, that's the same thing as saying 1 over y to the 3rd. Alternatively, if you have something like 1 over x to the negative 2, that's the same thing as saying x squared. All right, let me draw little lines between here. Cool. So that's the 3 concepts that this is playing with here. So let's just kind of attack it and get the answer. Okay, we have 2 ways we can answer this. We could do the exponent in fraction way or the negative exponent way. I'm going to do both so you can see how it works. First way, exponent in fractions. We know we have our b to the 9th times 1 all over b to the negative 5th. That's like saying b to the 9th over b to the negative 5th. And so we're dealing with exponents, same base, and division, so we're going to subtract. So that's like saying b to the 9th minus a negative 5th. So what are we going to get here? We're going to get b to the 14th. The second way that you can do this, you're going to get b to the 9th times 1 all over b to the negative 5th. That's the same thing as saying b to the 9th over b to the negative 5th. Now we're going to use the negative exponent way here. So we're going to bring this up to the numerator and make it positive. That's like saying b to the 9th times b to the 5th. And just like division means subtraction, multiplication between exponents means addition. So what we're going to get is b to the 9th plus 5, and we get the same answer, b to the 14th. Frankly, a kind of intimidating looking problem with that negative exponent and this property you need to be aware of. But really, if you can master these 3 concepts, you can knock this problem out pretty easily, I think. So just keep in mind that 0 exponent is always going to equal 1. The exponent in a fraction is the same thing as subtracting those exponents, as long as they have the same base, right? And then negative exponents, you just flip it and put it underneath a fraction and make it positive, or if it's in the bottom denominator, you put it in the numerator and make it positive, just like here. Because really, once I put it in the numerator, this is just over 1. Now we're going to talk about the last thing that you have to be aware of, and it's scientific notation. Okay, so now we're going to get into the last kind of exponent D thing. Okay, so what is scientific notation? It's for really big numbers and really small numbers. They use a lot in like space travel and stuff just because the distances are so far, you know what I mean? Here are 2 examples of scientific notation. The way to do this is just to focus on this number up here because this is going to signify how many decimal places you move. Positive, just like a number line, positive goes right, negative goes left. We need to move this decimal place 5 spaces. 1, 2, 3, 4, 5, and then we put our decimal. Now we need to fill in the rest of this, and every one of these dips needs a 0. Cool. So that's our answer here. This is 540,000, and that's what this represents. And then you have really small numbers, 2.7, and then we need to move this decimal place left, because it's negative, 8 times. 7, 8. We put our decimal place, and then we fill in with zeros. Okay? Very small number, right? They're going to give you something like this. So we're dealing with exponents, we're dealing with scientific notation. The way to do this is to focus on your numbers first, and then to focus on your exponents second. So really, another way to say this problem is 5.4 divided by 2.7. Okay, cool. So this is going to equal 2. And now we need to do the exponents here. Now, remember, when exponents with the same base are divided, you can subtract. So that's like saying, I guess, times 10 to the 5 minus a negative 8. So our answer is going to be 2 times 10 to the 13th. Focus on your constants, then focus on your exponents. Since it's 10, they share the same base, and you can do a lot of this just with straight subtraction, which is what we did here. And you get 2 times 10 to the 13th. Okay, so this is how you do all of the kind of exponent, radical, scientific notation stuff. If you have any questions, you can leave them in the comment section below. Check out my website, tylertutor.com, for classes and private tutoring, and just for like free kind of quizzes and stuff like that. There's like a lot of stuff you can do on the site. I probably spend way too much time on it. If you like the video, leave a like. Good luck, guys, with all of your studying. And if you have any questions, I'm here to help.